Seeing as when we were going through this in the previous video, it wouldn't let me go between the slideshow and the periodic table, I just wanted to add a little something so you can definitely make the switch between the two and see what I'm actually pointing at when I point on the screen. So when we look at this, this is an outline of the periodic table, and instead of trying to memorize off bow and the order in which all these shells fill, especially when you get to something like 4s followed by 3d, the periodic table trend is much easier to figure this out. So we can see that the S block is down the left-hand side of the periodic table. So these two columns are the S block. And the S block starts at 1s, so hydrogen and helium would fill the 1s's. Lithium would begin the 2s's, the 3s's, 4, and so on. Anything in the first column would have the superscript as S superscript 1, and then if it's in the second column, or helium, would be S superscript 2. So barium, for instance, its very final part of its electron configuration would be 1, 2, 3, 4, 5, 6, S2. Over here is the P block, so all this orange stuff. And we know we can have 3 orbitals in the P's, and each one can contain 2 electrons. And so 3 times 2, that'd be 6. In the P block, if we count how many elements we have 6. So that's perfect. This would be a P1, P2, P3, P4, P5, P6. We also know that the p orbitals don't exist for n equals 1. So boron would be 2p1, and these would be the 3p's, 4p's, 5p's, and 6p's. So S's start on 1, P's start on 2. The transition metals are the D block, and they start on 3D. So S's start 1, P's start 2, D's start on 3. And that's the easier way to remember that this is 3D and this is 4s. So it helps you remember that off-bow principle without memorizing anything. So scandium would be 3d1, zinc would be 3d10. This would be our 4ds and our 5ds. And then our last PowerPoint kind of talked about, we won't really be looking at the F block, the stuff at the very bottom that you probably never really have used in any other course. But we know that the F's have 7 different orientations. Each orientation of those orbitals can hold 2, and we could count across 1, 2, 3, 4, 5, 6, 7, all the way to 14. So that makes sense as to why the F block is 14 elements across, because there are 14 spots for electrons within the F orbitals. So that's kind of the comparison that I want to show you as to how to use this instead of remembering any of those off-bow principle diagrams. And let's just kind of use it for the next few slides pretty quickly. So gallium, we're trying to find the electron configuration of that. Gallium is right here. So it's in this wedge. We know that's the P block. It's the first one in the P block, so we know it'd be P superscript 1. P block starts at 2p, 3p, 4p. So gallium's going to end in 4p1. We just have to label everything up into that point. So gallium's number 31. We have to make sure we have, if we were to count all of our superscripts, 31 electrons. So they're always going to start the same way. So we have to get through the 1s's first. So that'd be a 1s2, 2s2, come over here. Here's the 2p, 2p6 all the way across, 3s2, all the way across these ones, 3p6, we're at 18 now, 4s2, remember that the d's start at 3, 3d10, all of them, and the last one, gallium, 4p1. So if we want to do the entire electron configuration, we'd have to run that entire string of numbers and letters. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So that's gallium. We can, and hopefully this was pretty obvious in the last one, condense that, because if you keep doing that and you're always starting at 1s2, 2s2, it gets pretty repetitive, and it's a great way to remember things and kind of build comfort level with that, but it gets tedious. So the best way to do that is called condensed electron configuration, or you'll also hear it called the noble gas configuration. So that short form just pretty much says wherever the last noble gas was, and it'll always end in a P6, because we'll see that trend, right? All of the noble gases, except for helium, will end in a P6 because that's where they are on the periodic table. So that's kind of gets cropped off, and we'll put in square brackets whichever noble gas that ended up being. So it has to be a noble gas that is already surpassed in the periodic table. And by that I mean when we're looking at chlorine, which was the example in the slideshow, even though argon's right here, we have to shorten it with neon, because neon is within the electron configuration. Anything further, anything with more electrons on the periodic table wouldn't be part of its electron configuration. And the reason for that is just if we were to ionize or do something to chlorine, pretty much the noble gas won't be touched because it's stable. So all of those electrons can kind of be pushed aside, and we can only look at the ones that are afterwards, ones that maybe could be ionized. Something a little bit bigger, because obviously chlorine didn't make you write too much, would be tin. And let's see, there's a P6, there's a P6, there's a P2. So the last P6 was 4p6. There's 2p6, 3p6, 4p6 was krypton. And then the only things we have to keep going for would be anything afterwards that leads us to tin. So our B is 1, 2, 3, 4, 5 S2. We got through all the D's, which would have been the 4 D's, 4D10. And then 1, 2 in is tin, and it is 2, 3, 4, 5, 5p2. So it's a little bit less to write, but it also makes sure that you know how to use electron configuration before you go this way. And then the last two slides were about ions. Pretty much the easy ones would be if you're doing anions, if you're adding electrons to your configuration, because honestly all you're going to do is, say if we're looking at bromine, we're adding an electron, so we're pretty much going to be writing the electron configuration of krypton. So just add an electron, so instead of being a P5, it's going to end in P6 now. The hard ones are cations, so if we're taking away electrons, because there's just a little bit of an extra task to that, because we're only going to be taking away electrons from the highest quantum number. So sometimes that's going to be what's at the very end of your electron configuration, the whole string of numbers and letters you're writing. But because sometimes we'll have a higher quantum number here, we'll have a 4s versus a 3d, we might have to be taking away electrons that aren't at the very end of our configuration. So we were looking at gallium 3+, so we're taking away 3 electrons, and we can see that we have a 4p here, and then we'd have 3 Ds, and then 4 S's, right? So we'd have to keep all the 3 D electrons there, because they're a lower principal number, a lower n value, than these 4 S's. So when we take them away, we'd actually have this 4p1 gone and these 4s2's gone, but remain to have 3d10s within our electron configuration. So I just want to add that on, seeing as you weren't able to see me go back and forth between a periodic table and that PowerPoint.